Hello, my name is郭光輝.
Hello everyone, my name is Zhang Kaishen.
And in this video, we're going to present our topic, Dysgraphia handwriting classification through machine learning. So starting off, dysgraphia is a disorder affecting the written expression of symbols and words. It shows the signs of late brain development. The goal of our model is to detect dysgraphia potential by taking handwriting images as the inputs. We prepared 3 models and pre-processed our dataset, and from there, we will see which model and input type performs the best. So here's our motivation. Here are some related work.
Okay, so this is the open source datasets we found it, and it's gathered through the data collection techniques carried out by the primary school students and children undertaking intervention at the Malaysian Dyslexia Association. So it's determined by the authority whether the handwriting had potential or low potential or not. So for low potential dysgraphia, we have 135 images, and the images is including with the potential close to 0 as confirmed by the author. And for potential dysgraphia, we have 114 images. And the next one will be the data preprocessing part. We want the single word image as one of the research part, so we're doing pre-processing. So for all the sentence image are cropped into the separate words with the settings of left and right margin of 5 pixels and the top and bottom margin of 2 pixels. So after the cropping, we will be having 1,507 image for the low potential dysgraphia and another 211 image for the potential dysgraphia. And the methods for our experiment is to find out the best model for the dysgraphia classification. So we will be testing out 3 different models, which are VGG16 and ResNet50, and also a custom CNN model that we'll be introducing later. So we are going to test out the models using 6 different image inputs as shown in the PPT. So for our dataset, we will be using 60% of the image for training, another 20% for the validation, and the remaining 20% for the testing. So this is the experiment and the result. The first one will be the performance of the VGG16. So as you can see in the table, the sentence plus word is providing the highest score, and this is because the dual input helps the model capture additional context that neither the sentence nor the words inputs could achieve alone. So I'll be talking about the impact of the augmentation. So adding the augmented data is generally lower the performance across words and the sentence word inputs, but not for the sentence input. So the sentence type is benefits from the augmentation because it's introducing the variability to the model, so it's allowing it to learn the generalization better. But for the words type, it's less complex but more sensitive to the noise. So adding variability to the dataset is reducing the noise that disrupts the model's ability to generalize effectively. But for the sentence plus word input, the word level augmentation may not add enough the meaningful variety to improve the generalization of the model. The next one will be the ResNet50. So as you can see in the table, the word-only image with the augmentation is having the best performance. Because the ResNet50 performs more optimally on simpler and the focus inputs like the word-only data. So for the impact for the augmentation, for the sentence input, the performance decreased significantly because it's introducing variability that struggles the model to interpret correctly. But for the word input, the model has mainly learned the variability from the word image data. So the augmentation doesn't affect much. But here, the overall performance score is still having the augmentation with it. So for the sentence plus word input, the sentence image augmentation is reducing unnecessary variability that lowers the model's ability to generalize across both inputs.
So here are some details on the custom CNN model. So it has 3 convolutional layers with increasing filter sizes, followed by a dense layer with 512 units and a single output layer. And the structure is sequential with simple convolutional layers and max pooling. And here's some results from the CNN model. For the analysis on the custom CNN model, first of all, it is shown that the sentence images as input performs the best with this model. So a whole sentence provides the model with structural information and patterns linked to dysgraphia potential. Words, on the other hand, lack structural information, which reduces the model's ability to reliably detect positive cases. Now, the data augmentation benefits word images, but not sentences. This suggests that augmentation hides crucial indicators related to sentence structure. On the other hand, augmentation on words helps the model recognize dysgraphia-relevant variations in letter formatting and spacing without affecting sentence-level structure. Combining words and sentences as input only slightly improves the results compared to word input. The mixed input adds complexity but lacks sufficient consistency in detecting these features across both words and sentences. The same goes for when sentence and word images inputs are combined in the augmented data. Now, here's a quick analysis on all of the models. So the custom CNN model is shown to be shallow and simple compared to VGG16 and ResNet50. More layers help capture more details on features, thus showing why VGG16 and ResNet50 perform better when given word image inputs. Fewer layers can generalize features without focusing on excessive detail, hence why the custom CNN layer performs better when given sentence image inputs while containing diverse handwriting patterns. Shallow models are better at processing augmented inputs from simpler images than deeper models. And VGG16 benefits specifically from sentence-level augmentation because the images have complex features that VGG16 can't leverage with its architecture. And then for our conclusion, I will display it over here. Finally, for our future work, we want to implement a visualization technique to study dysgraphia characteristics on the handwriting image. And we want to do research on each combination of the augmentation techniques to see which best supports the model. That's it. Thank you for watching.
Thank you, everyone.